Streamlines in fluid mechanics. So by definition, the equation for a streamline is equal to the derivative of y with respect to x, which can also be expressed as the ratio of the velocity vector's components, also equal to the negative ratio of the reference point's shift in the y direction to the x direction, which can also be expressed as just minus y over x.
And here's a quick look at the flow of the river.
We'll talk about more detail later, but you can see some turbulence forming, some vortexes coming out of that, some laminar flow, and the transitions between the different flows within the river.
Alright, so we have a definition of a streamline. A streamline is a line which is tangent to the velocity field on every point on the line. As you can see in the video earlier, this is an example of a steady flows, which mean that the streamline do not change shape as time progresses. This is also a two-dimensional flow, which then can define the slope of the streamline equal to the tangent of the angle that the velocity vector makes with the x-axis. And you can see the equation earlier.
If you were paying attention to the video earlier, you can see that there are several vortexes, or vortex rotations that start to form and rotate counterclockwise. This takes the form of circulation around the bumps of the bottom surface. Thus, each bump is representing a solid body or an airfoil. The vortex happens when there is a disruption in the velocity. This phenomenon is common in aircrafts, ships, rivers, and etc. And right here you can see the vortex, and it's starting to curl counterclockwise. At first the flow appears to be laminar, but as the flow develops, a turbulent region forms and the vortex begins to form. From the side view, it can be seen that the shear force that occurs at the separation of boundary layers from the solid object creates the vortex.
Alright, as you can see earlier in the video, there were laminar flow, and what it is the fluid flows in parallel on the top of the surface. This means that the layer between each other do not have disruptions in between.
In the video, you can also see turbulent flow. This happens when the initial force causes the circular whirlpool in the flow, and it creates turbulence. And here you can really see a clear difference between laminar flow and its transition to turbulent flow.
Alright, so we have a comparison of a laminar flow versus turbulent flow. With that, we use Reynolds number to figure out if it's either laminar flow or turbulent. If we calculate the Reynolds numbers and it's less than 1,000, that means it is a laminar flow. But if it's greater than 10,000, then it is a turbulent flow. And we'll show you what happened in between when it's not 1,000, less than 1,000 or greater than 10,000.
here in this picture, you can see the laminar flow at the beginning with a Reynolds number of less than 1,000. And at the very end, you can also see the turbulent region, which has a Reynolds number of greater than 10,000. And in between the 10,000 and 1,000, there's a transition zone where either laminar or turbulent flows can occur.
All right, here's a little history of where Reynolds number come from. And it's this guy, Oxbourne Reynolds. He derived Reynolds numbers and was the first to show that the numbers combination of the several variables resulting in a dimensionless number and could help distinguish fluid flow into two types, laminar and turbulent. Using dimensionless number, using dimensional analysis, you can you can find a common relationship between the fluid's density, velocity, length, and viscosity to determine Reynolds numbers. And here's the video of the river that we shot earlier.
And we'll just point out a couple more things in more detail here. You can see at the beginning of some of these flows, the flow is clearly laminar, and as it develops, it transitions into the turbulent flow. In between, there's the transition area, and Reynolds number comes into play to determine which type of flow it'll be. And here you can actually see it in real life. Looking for some vortexes here.
You could find one right here, kind of. And it's kind of hard to see. It's a steady night.
Maybe we'll get a good one. Right there, you can see a small vortex coming through, and that just happens in the turbulent zone. You should never see a vortex in a laminar
it's right there
zone.
as well. You can see the bubble there; it's just swirling around. There's a bunch of turbulence, and there's this laminar right there. All right, and that's what we have for today.
Thank you very much.